Welcome you all in this 8th lecture on metric spaces. And the last time in the previous talk, we have seen that the arbitrary union of open sets is open and finite intersection of open sets is open. However, the arbitrary intersection of open sets need not be open. Now, today we will see that some other properties of the open sets and the interior of a set. So, suppose you have A is your non-empty subset of a metric space X, then the interior of A is the largest open subset of A. That is to say, so there are two things. One is the interior of A is the largest and second is open. So first we will have to prove that interior of A is an open subset of A, and then we will have to prove that it is the largest open subset of A. So first of all we shall prove that interior of A is an open set. So to prove that interior of A is an open set, we have to consider an arbitrary element X in the interior of A, and we must prove that it is the center of some open sphere contained in this interior of A. Okay, then by the definition of the interior of A, there exists an open sphere SRX, this open sphere with center at X contained in A for some R is equal to greater than 0. But SRX is an open set, as we have proved that every open sphere is an open set. So SRX is an open set. So for each, you see, for each X, this is a subset of X. So for each of its point is the center of some open sphere contained in SRX and hence contained in A. And therefore, each point of SRX is the interior point of A. That is the SRX, okay, the open sphere with center at X radius R contained in the interior of A. It means that X, which we have chosen arbitrary, is the center of some open sphere contained in A, and therefore interior of A is your open set. Now we have to prove that it is the largest open set. So suppose that B, which is a subset of A, is another open set. Okay, B is your any arbitrary open set, and let us take small x is an element of B. So we want to prove that this B is nothing but it is a subset of interior of A. Okay, so then because B is open, so there exists an open ball. Okay, because X is in B and B is open, so this must be a center of some open sphere contained in B. So there exists an open sphere SRX contained in B, but B is what? B is a subset of A. It means that X is the center of some open sphere contained in A. It means what? It means that X is an element of interior of A. So what we have taken? We have taken X is in A, but X lies in interior of A, and therefore B is a subset of interior of A. So if you take any open set, that must be a subset of interior of A, and hence since interior of A is open, interior of A is the largest open subset of A. Okay. Then we have a remark which says that interior of A is the union of all open subsets of X. So if you take the interior of you take the union of all open subsets of A, that would be your interior of A. Now here I have several exercises and you must try to do all these exercises. Suppose in a metric space X, the two balls with different centers and different radius are same. Okay, the two balls with R and S. Okay, with two balls R and S and two different centers and different centers and different radius for some x's and some positive numbers SR. We don't know whether they are same or not. Can we say that if the ball is the open sphere SRX is equal to the open sphere SYS, okay, they are same, then the centers must be same? Or can we say that the radius must be same? You can do it, you can get the answer very easily by considering the discrete metric space. I am not going to give the detail, otherwise it is not an exercise for you. Okay. So, the second is one, here is you can prove that the interior of A is equal to interior of A. This is very simple one. And in Rn, let capital R denote the set of points having only rational coordinates and I its complement. Then the set of points having at least one irrational coordinates. Okay. Okay, that is the set of points having at least one irrational coordinates. Then prove that interior of R equal to interior of I, which is equal to empty set. The second is that prove that if you have R is less than R dash, then prove that this set is what? If you remove this one, you consider only this one, okay, you consider only this set, it means what? You will get a disk, and this is outside the so here is this set is an open set. So this you have to prove. As I have mentioned that if D is a metric, then D star, which can be defined in this way, is also a metric. Now, we will have to prove that if you have an open set with respect to the metric D, would it be an open set with respect to the metric D star? Okay, so you can see that here is proof that the family of open sets with respect to the metric D is same as the family of open set with respect to the metric D star. And later we will see that basically D star and D are equivalent matrices, and therefore their family of open sets are same. So this we will see, but here you can try by yourself right now. And let's see, here is this very important thing, this exercise is very important and very useful basically. If you have a metric space X and you have two distinct points X and Y, then you can always find two disjoint open balls with center at X and radius center at X and center Y. So prove that there exists disjoint open sphere centered on X and Y. So this you can prove very simple way. So you can consider, for example, you can take any 2 point. Suppose you have a point X is here. Okay, you have a point. So you have a point, this is your point Y, okay, and suppose the distance between this distance is your 3R. So this distance is your 3r. 3r. So you can take an open ball, okay, with radius r, and here you can take an open ball with radius r, and then you see this is your SRx and this is your SRy, and of course the intersection of this is empty. So you can find these two things. And similarly, you can have you can prove that these sets, this set is open and this set is open. Okay, and then we are now going to see the concept of closed sets and closure of a set. So before defining the closure of a set or closed set, we have to define the limit point or accumulation point or cluster point of a set. So suppose you have, this is your metric space. I just mentioned metric space may not be a rectangular shape. So just I made it's a metric space, and here is a blue color line is a subset of x. Okay, and take a x, a point, okay, which of capital X. The point x may not be a point of A. So this point x, small x, is a point of x, and this point x is called a limit point of the set A. If each open sphere centered on x contains at least one point of A other than x. So you have at least, so each open sphere, so either you take this open sphere or the smaller open sphere or the bigger open sphere, any open sphere, so every open sphere centered on x contains at least one point of A other than x. If, of course, if x is a point of A, then other than. If x is not a point of A, then it contains points of A. Okay. So then you can write this in this way, that the point x is a limit point of A if SRx, the open ball with center x, minus x intersection A is non-empty for all r is greater than 0. Keep in mind, in the interior of a set, we are saying that it is the center of some open sphere contained in it. But for the limit point, for it is the each open sphere, every open sphere centered on x contains a point of A other than x. So that is the main thing. For example, suppose we are taking, here is, suppose you have, this is your set. Again I am making rectangular type. This is your set x. Okay. So here is, this is your set A. Let's take, here you have a point x. Okay. Whether this point x would be a limit point of A or not. So if you take an open sphere, okay, this is your open sphere centered at x and radius, suppose this is your radius r. The intersection of this SRx, intersection A, is equal to empty, is not non-empty. Okay, because and if you consider like this, open sphere, this is your open sphere, but the open sphere now it is it contains, but the question here is that every open sphere centered on x, but this open sphere centered on x contains a point of A other than x, but this open sphere does not contain any point of A. So this point is not a limit point of A. Okay. So this is a very important thing. You have to check it very carefully. Okay, and then you see that a set of all limit points of A is called the derived set, and it is denoted by A prime. So set A prime is the set of all limit points of A. Okay, then let us have some examples. So again, I am considering the usual metric space R, okay, and A set which consists 1, 1 over 2, 1 over 3 and so on. Then what would be the derived set of A? So you look here is, suppose you have, this is your real line, okay, and you have 1, and then you have 1 over 2, and then 1 over 4, and there is 1 over 3, and 1 over 5, and 1 over 6, and so on and so on, and then you can go up to here is 1 over n. Okay. Look here is, whether 1 over 3 or 1 over 2 or 1 over 4, they are the limit point of A or not. If we say that this is the limit, then it should be, now what would be the open sphere? Open sphere with center at 1 over 3. Radius, this is your radius R, okay, does not contain any point of A other than 1 over 3. And so 1 over 3 is not a limit point of A. And similarly, you can check all the points, they are not the limit point of A. For example, if you are considering here is, you consider a point 1 over this one, whether this is a limit point of A. No, this is not, again is not a limit point of A, because you can consider the difference after that, okay, you can consider a point whose the radius with less than the distance from 1 to this one, okay, and then you will see, suppose this is the point 1 over 1, 1 over 10 raised to the power something, so you can take any open sphere whose radius is less than 1 minus the distance between this and this, must be the radius is less than the distance between this and 1, and then it will contain only the point 1 over this point, not the other point. And similarly, you can see that sorry, we go here is, sorry, this is your 0, so not here. This is 0, sorry, this is 0, this is 1. This is 0, this is 1. So here is, now if we take this 0, whether 0 is the limit point of this set or not. So if 0 you can consider, then you can always find this 0 always contains whatever is your radius, it will contain some point of A other than the 0. But keep in mind, 0 is not an element of A. So no matter, because the point x is, there is the point x is in x, not in A. Okay. So this point x in A is called a limit point. So 0 is the limit point of this set, and no other point of this set, okay, are limit point of, so limit point of A. Similarly, you can see that if A is equal to set of natural numbers or set of integers, then no point of A or no point of Z or no point of R are the limit point. How it is, you can see, you can see that suppose I consider this is your, suppose here is, let us take integers, so let us take natural numbers. So here is start, you can take 1, you can take 2, 3 and 4 and so on. Okay, check whether this point is a 3 is a limit point of the set of integers. So if you take this is point set of integers, so I can consider this is my radius R and this is your open ball. So this is your SR3. Okay, but SR3 does not contain any point of n other than 3. Okay, but in the definition of the limit point, each open sphere centered on 3 contains at least one point of n other than 3. So it does not contain any point of n other than 3. So 3 is not a limit point of n. Similarly, you can see that 1, 2, 3, 4, any number is not a limit point of n. Okay. Now, what about the other points? Because A is a subset of R. So let me take, suppose I take a point is here, okay, half. Okay, whether half, which is not a point of A, okay, which is not a natural number, whether it would be a limit point of A. So if again you can take, here you can make, this is your SR half, okay, this is your radius R, okay. So with this radius R, this open sphere with center at 1/2 and radius R does not contain any point of n. So it means that 1/2 is not a limit point of n. Similarly, you can prove that no point on the real line is a limit point of n or limit point of integers. Okay, and therefore the drive set is equal to empty set. So this way you can prove that the drive set is your empty set. Okay, now let's take if A is the set of rational numbers or irrational numbers. Okay, then the drive set is equal to R. How it is? You can see again, suppose you have, this is your real line, okay. So after each rational number, you can find an irrational number. So if you will look, here is the set of rational numbers, or if you are taking set of, suppose you take set of rational numbers. So if you take a set of rational number, you have a point x, okay. Take whatever the radius you want, okay. Maybe it is 1/1 trillion. So because after each rational number you can find an irrational number, so whatever is your radius, okay, whatever is your radius, this open ball SRX will contain infinitely many points of this line. Okay, so this point is your limit point. And now suppose this point is your irrational number. If this point is irrational number, then again this will contain the open sphere with center at x and radius r will contain infinitely many points of q other than of q, and therefore this x is a limit point of q. So all the points on the real lines are the limit points of q, and similarly you can prove that all the points on the real line are the limit points of set of all irrational numbers, and therefore the derived set of the set of rational numbers or set of rational numbers is the whole real line. Okay. And now take every point on the real line is a limit point. Okay, so you can see that the derived set of R is equal to R, and if A is the Cantor set, then the derived set of the Cantor set is equal to itself. And in the discrete metric, if A is a subset of the discrete metric space, okay, then A has no limit point. A has no limit, since every open sphere of radius 1 consists only the center, and thus the derived set of A is empty set. Okay. Keep in mind the derived set of A is your empty set. Now, we can have a remark which says that by the definition of a limit point, we follow that any open sphere centered at a limit point of A must contain infinitely many points of A. Okay, what was the definition of the limit point? Limit point was the definition. Every open sphere centered on X contains at least one point of A other than X. But you will see that it will not contain only one point of X other than X. It will contain infinitely many points of A. Okay, so here is from the definition we can say that a limit point of A, any open sphere centered on a limit point of A must contain infinitely many points of A. That is, for each X, this a point X is a limit point of A if the intersection of open ball with radius R center X, intersection A, is an infinite set for each R is greater than 0. Okay, this you can see that this contain a point x1, okay, other than x. Then by the definition, the distance between x and x1, suppose it is equal to R. Okay, and then the open sphere with radius this, okay, consists a point x2 other than A from X, then and x2, then okay, continue in this way, you will get that SR1X contain infinitely many point of A different from X. So you can continue in this way. Now note that a limit point of A is not necessarily a point of A. As we have seen in the previous example that 0 was the limit point of this set, which is not a point of A. Now, in view of above this remark, we have the following definition. Okay, so a point X, okay, a point X in capital X in the metric space X is said to be an isolated point of A. This is said to be an isolated point of A if there exists an open sphere centered on X which contains no point of A other than X itself. No point of A other than itself. That is, SRX intersection A is equal to X for some R is greater than 0. So it means what? It means that as we have seen that if you consider the set of all natural numbers or set of all integers, okay, so set of all natural numbers, for example, you have this is your set of all natural numbers, so you have 1, 2, 3, 4, 5, okay, so this you take any ball, this is your open ball, radius R, SRX, okay, and this SRX contains only the point of N, no other point of A, and therefore this point is called an isolated point of A. Okay, so it may be a point, so this is your isolated point of A, but no other point of this. So here is if X is not a limit point of A, then it is an isolated point. Okay, so this is very important remark. If X is not a limit point of A, then it is an isolated point. Hence, every point of a metric space X is either a limit point or an isolated point of a set X, of a set A. Okay, so if A is a subset of a metric space, okay, then every point of X would be either a limit point of A or an isolated point of A. Now, consider an example So I am considering again the metric space X consisting 0, 1, 1 over 2, 1 over 3, 1 over 4 with the usual metric space of absolute value. That is, keep in mind, I am not considering X as a subset of R. Here is the very important thing is that I am considering X is a set consisting these element, okay, but it is not a subset of R. I am not considering as a subset of R. And then I am defining a metric on this X by dxy is equal to mod of X minus Y. Okay, so X and Y, small xy would be these elements. Okay, with this one, we can see that 0 is the only limit point of X. Okay, so 0 is the limit point of X, while the other points are the isolated points of X. Now, what will happen? So, sometimes you will see that if you are considering the metric space or a subspace or subset of a metric space, the limit point would be the same, but sometimes it may not be. For example, if we are considering this as a subset of R, then if we consider this as a subset of R, okay, with the usual metric, then we will see that 0 would be the only limit point of this set and other points are the isolated point. Now, we have like interior, so here we have the closure. So, the closure is let A be a subset of a metric space X, okay. Okay, now I stop over here. So, we will continue in the next talk about the closure of a set. So, thank you very much.